أهلا بالجميع، مستعدين لرحلة استكشافية في عالم الدوال المركبة العجيب؟ اليوم راح نغوص في أعماق الفصل السادس من الكتاب الكلاسيكي لبراون وتشيرشل، المتغيرات المركبة وتطبيقاتها.
يعني العرض اللي راح تشوفوه اليوم هو بمثابة خريطتنا البصرية للمفاهيم الأساسية في هذا الفصل، الرواسب والأقطاب. خلونا نبدأ ونفكك هالمفاهيم سوا، فكرة ورا فكرة.
طيب، خلونا ندخل في صلب الموضوع مباشرة. السؤال الأهم هو إيش يصير لما الدالة تنهار؟ تخيلوا معي إن الدالة هي خريطة للمستوى المركب. طيب إيش يصير لو لقينا قطع في هالخريطة؟ النقطة المهمة هنا إن هذا القطع مو مجرد خطأ أو فشل، بالعكس هو نقطة مثيرة جدا للاهتمام، نقطة تكشف لنا أعمق أسرار الدالة.
تمام. في المحطة الأولى من رحلتنا رح نحدد ونعرف بالضبط إيش هي نقاط الانهيار هذه على خريطتنا. هذه هي الأماكن اللي سلوك الدالة فيها يصير غريب ومثير للاهتمام بشكل خاص.
رياضياً العلماء يسمون هذه النقاط نقاط شاذة معزولة. عشان أبسطها، تخيلوها كأنها نقطة فوضى وحيدة وسط منطقة هادية ومرتبة على الخريطة. يعني كل شيء حولها تمام والتصرف طبيعي، لكن عند هالنقطة بالذات يصير شيء مميز وغريب.
وهنا تبدأ المتعة الحقيقية. راح نصنف هذه النقاط الشاذة بالضبط مثل ما المستكشف يصنف الكائنات الجديدة اللي يكتشفها. كل نوع له سلوكه الخاص وله قصة مختلفة تماما يحكيها لنا. عندنا 3 أنواع أساسية. النوع الأول هو النقطة القابلة للإزالة، وهذه مثل حفرة بسيطة في الطريق نقدر نصلحها بسهولة. النوع الثاني وهو الأهم في رحلتنا اليوم هو القطب. تخيلوا القطب كأنه بركان هائل، بركان يخلي الخريطة تمتد للما لا نهاية وقيمة الدالة تنفجر. والنوع الثالث والأخير هو النقطة الجوهرية، وهذه زي الدوامة الفوضوية، سلوك الدالة عندها يصير غريبا جدا ومستحيل نتوقعه. طيب، من بين كل هذه الأنواع تركيزنا اليوم راح يكون على الأقطاب، أو زي ما سميناها البراكين. ليش؟ لأنها هي المفتاح اللي راح يخلينا نفهم قوة حساب التكاملات المركبة اللي راح نتكلم عنها بعد شوي. حلو، كل قطب أو كل بركان له شيء نسميه رتبة ونرمز لها بالرمز M. فكروا في هذه الرتبة على أنها مقياس لقوة البركان، أو بتعبير أدق هي اللي تحدد مدى سرعة انفجار الدالة ووصولها للما لا نهاية كل ما قربنا من هذه النقطة.
والآن نوصل لمرحلة الاكتشافات المثيرة. اتضح أن كل نقطة من هذه النقاط الشاذة تخبي جواتها سر على شكل رقم سحري، وهذا الرقم هو مفتاحنا عشان نفهم القصة كاملة.
طيب، كيف نلاقي هذا الرقم السري؟ هنا يجي دور أداة قوية جدا اسمها متسلسلة لوران. هذه المتسلسلة هي اللي تسمح لنا نزوم ونشوف داخل النقطة الشاذة، هي المجهر الرياضي حقنا اللي يكشف لنا كل التفاصيل الدقيقة. لما تشوفوا هالمتسلسلة لا تخافوا من كل هذه الرموز. الجزء اللي يهمنا فعلا هو اللي يسموه الجزء الرئيسي، يعني الحدود اللي فيها أسس سالبة. هذا الجزء بالذات هو اللي يوصف لنا بالضبط إيش قاعد يصير عند النقطة الشاذة، هو اللي يكشف لنا طبيعة البركان أو الدوامة اللي تكلمنا عنها. ومن بين كل هذه الحدود في واحد بس هو بطل قصتنا، واحد بس هو الرقم السحري اللي ندور عليه، وهو الراسب، المعامل اللي اسمه B1. هذا الرقم الصغير البسيط يلخص لنا كل شيء، هو جوهر النقطة الشاذة، هو بصمتها الخاصة اللي تميزها عن غيرها. والشيء المدهش هو إن هذا الرقم الوحيد، هذا الراسب، هو اللي راح يفتح لنا الباب لمعرفة قيمة رحلة كاملة، قيمة تكامل كامل حول مسار مغلق. يعني هو المفتاح السحري لحل مسألة تكامل تبدو معقدة جدا. شوفوا هالعلاقة بسيطة بشكل مذهل. التكامل للدالة حول نقطة شاذة واحدة هو ببساطة 2 باي آي ضرب الراسب حق هذه النقطة وبس. تخيلوا، ربطنا سلوك الدالة في نقطة صغيرة جدا بقيمة التكامل على مسار كامل حولها. شيء عبقري. الحين خلونا ننتقل للاختصار النهائي، للضربة القاضية، النظرية العظيمة اللي راح تجمع كل اللي تعلمناه في أداة واحدة خارقة. وهذه هي قمة رحلتنا اليوم. لكن أكيد في سؤال يطرح نفسه. طيب، إيش يصير لو المسار حقنا ما يحيط ببركان واحد بس؟ لو كان يحيط بمجموعة براكين ونقاط شاذة، هل الوضع يصير معقد أكثر؟
الجواب وبكل بساطة هو لا. وهنا يجي دور الكنز الحقيقي لرحلتنا، نظرية الراسب لكوشي. النظرية هذه تقول لنا إن قيمة التكامل الكلي هي ببساطة 2 باي آي ضرب مجموع كل الأرقام السرية، يعني نجمع الرواسب لكل النقاط الشاذة اللي جوا المسار وخلص. القوة والأناقة في أبسط صورها.
طيب، كيف نستخدمها عملياً؟ الطريقة سهلة جداً وفي 4 خطوات بس. أولاً، نحدد المسار اللي رح نمشي عليه. ثانياً، ندور على كل النقاط الشاذة اللي جوا هذا المسار. ثالثاً، نحسب الراسب أو الرقم السحري عند كل نقطة. ورابعاً وأخيراً، نجمع كل هذه الرواسب ونضرب الناتج في 2 باي وانتهينا.
لاحظتوا التحول العجيب اللي صار؟ حولنا مسألة تكامل على مسار متعرج ومعقد لمجرد عملية جمع بسيطة، وهذا هو جوهر جمال وقوة الرياضيات المركبة.
إذا كانت الأقطاب هي بوابات للما لا نهاية والرواسب هي مفاتيحها السرية، يا ترى إيش الأسرار الثانية اللي لسه مخبيها لنا المستوى المركب؟ هذا السؤال يخلينا دايما متحمسين نواصل رحلة الاستكشاف.
All right, today we're diving into something really cool, from complex analysis, residue theory. Now, this is one of those powerful tools that lets you solve problems that look, well, pretty much impossible. Let's just jump right in and see what I'm talking about. Okay, take a look at this thing. This is the beast we're going to tame today. It's an improper integral stretching all the way from negative to positive infinity. I mean, just looking at it is intimidating, right? Seriously, where would you even start? Exactly. If you're thinking back to your Calc 1 or 2 days, you might be thinking maybe partial fractions. And let me tell you, you would be in for a very long day. It's just a nightmare. But what if there's a better way? A kind of mathematical secret passage. So to find that secret passage, we have to completely change how we look at the problem. The big idea here is to get off this flat, one-dimensional real number line and step into the much richer two-dimensional world of the complex plane. And once we do that, once we imagine our integral as just one piece of a bigger path, or what we call a contour, in this complex plane, we suddenly get a whole new toolbox to play with. So let's think of the complex plane as our crime scene. The answer to our mystery is in there somewhere. We just have to find the clues. So what exactly are these clues we're looking for? Well, in the world of complex analysis, we call them isolated singular points. Just think of them as these specific little spots on our crime scene map where our function kind of misbehaves. It's not analytic, which is the fancy term for being nice and smooth. These are the hot spots, the places we absolutely have to check out. Right, but here's the thing. Not all of these singular points are created equal. They come in a few different flavors. And to stick with our detective story, let's call them our suspects. Our job is to identify these suspects and figure out what they're up to. So we've got 3 main types of these suspects. First, there's a removable singularity. You can think of that as a tiny pothole in the road that you can easily patch up. Then you have an essential singularity, which is just total chaos. It's a mathematical black hole. But the one we really care about, the third type, is the pole. And that's where things get really interesting for us. Yeah, for solving these big, hairy integrals, the poles are our prime suspects. These are the points where our function just goes wild and shoots off to infinity. And it turns out they hold all the crucial information we need to crack this case wide open. Now, it's really helpful to see how poles relate to something you're probably more familiar with, zeros. You know, a zero is just where a function hits the value 0. A pole is where it goes to infinity. And for functions that are fractions, they're basically 2 sides of the same coin. A 0 in the denominator, boom, that creates a pole. It's a super important relationship to keep in mind. Okay, so we've got our prime suspects. The poles. Now what? How do we, interrogate them? Well, it turns out each pole has this unique signature, kind of like a fingerprint. And this fingerprint tells us everything we need to know about how it affects our integral. We call this fingerprint the residue. So what is a residue, technically? Well, if you were to expand the function out into this special kind of power series called a Laurent series, the residue is just one specific number in that expansion, the coefficient of the 1 over z minus z0 term. I know, that sounds a little abstract, but just hang on to the main idea. It's a single number that acts as a unique ID for that pole. And this is where the magic really happens. All that complicated, swirling behavior of the function right around that pole, it all gets boiled down to one single number. That's it. This one number holds the key to everything. And check this out. Here's the connection, and it is just beautiful. If you were to integrate your function around a little closed loop that has just one pole inside it, the answer to that integral is simply 2 pi I times that pole's residue. That's it. It's this incredible link between what's happening at one tiny point and the value of an entire integral around it. Okay, that's great for one pole, but what if our path, our contour, has a bunch of them inside? Well, that's where the real powerhouse tool comes in. This is the master key that unlocks the whole mystery, Cauchy's residue theorem. Basically, the theorem says this: the value of the integral around that big closed path is just 2 pi I times the sum of the residues of all the poles you find inside the path. It's just so simple and elegant, it's almost hard to believe. So think about what this means. We don't have to do that difficult integral at all anymore. We just have to play detective. We find our suspects, the poles, that are inside our chosen path. We collect their fingerprints, the residues, add them all up, and multiply by 2 pi I. That's the answer. Seriously, case closed. All right, we've got our theory, we've got our master key. Now let's go back to that monster integral from the beginning and see how this theorem just completely demolishes it. So here's the game plan step by step. 1. Find all the poles of our function. 2. Draw a clever path or contour and see which poles are inside it. For problems like this, a big semicircle in the upper half of the plane is usually the way to go. 3. Calculate the residue for each of those poles inside. 4. Add up those residues. And 5. Multiply that sum by 2 pi I. And we're back at the scene of the crime. Our original problem becomes the complex function f of z equals 1 over z to the 6th plus 1. So where are the poles? Well, they're just the spots where the denominator equals 0. In other words, they're the 6th roots of -1. Now, there are 6 of these roots in total, but when we draw our big semicircular path in the upper half of the complex plane, it turns out only 3 of them are inside. You can see them right here. So these 3 are the only suspects we need to worry about. Okay, now comes the part where we calculate the fingerprint, the residue for each of these 3 poles. Now, we're not going to grind through all the algebra right here, but the calculation is pretty straightforward. And when you find the 3 residues and add them all up, you get this beautiful clean number, -I over 3. And now, the grand finale. The residue theorem says the integral over our whole loop is 2 pi I times that sum we just found. So that's 2 pi I times -I over 3. The i's multiplied to -1, the negatives cancel, and we get 2 pi over 3. Now, there's one little detail where you show that the integral over the big arc goes to 0, which basically leaves us with the answer to our original problem. And just like that impossible-looking integral is solved. So why should you care? I mean, what's the big deal? Well, this is way more than just a neat math trick. This technique, using complex analysis to solve real integrals, shows up everywhere. We're talking physics, electrical engineering, signal processing, you name it. It's this incredibly elegant shortcut for solving real-world problems that are otherwise just a total mess. And really, that just leaves you with a pretty cool thought, doesn't it? This whole thing felt like we were detectives on a case. We mapped out the crime scene, we identified the suspects, and we used a master key to crack it. It really makes you wonder, right? What other impossible problems out there are just sitting around waiting for someone to find the right tool, the right way of looking at them to unlock the answer?
You know, we usually think of numbers as living on a straight line, right? But what if that line was just one street in a huge hidden city? Well, today we're going to explore that city. We are talking about complex numbers, and you're about to see how they open up a whole new visual dimension in math.
We're all super comfortable with the real number line. You've got numbers going left, numbers going right. It's just one dimension. It's predictable. But what if that was only half the story? This question, right here, is the key that unlocks the entire world of complex numbers.
All right, so to answer that, we've got to go beyond the number line. See, there are some math problems, like what's the square root of -1, that just don't have an answer on that single line. So to solve them, we need to expand our thinking. We need to add a new dimension.
And here it is, the complex number. Look, at its heart, a complex number, which we usually call z, isn't really that complex at all. It's just a pair of 2 real numbers, an x and a y. The easiest way to think about it is like coordinates on a map. One number tells you how far to go sideways, and the other tells you how far to go up or down.
So this new map we're using, it's called the complex plane. And your familiar old number line is still here. It's the horizontal one, the real axis. But now we've added a brand new vertical line, the imaginary axis. So the x part of our number moves us left and right, just like always, and the y part now moves us up or down. Just like that, every number has its own unique spot on a 2D surface.
Okay, let's just nail down the terminology for these coordinates. That x value, we call that the real part of z. The y value is the imaginary part. So, what happens if a number's real part is 0? Well, it means it lives only on that vertical axis, and we have a name for that. It's a pure imaginary number. So, we've established that complex numbers are basically points on a map, but we can unlock even more power by seeing them in a slightly different way. Let's start thinking of these numbers not just as locations, but as vectors, as arrows drawn from the center of our map straight out to that point.
This means every single complex number, z, can be pictured as an arrow that points from the very center, the origin, out to its coordinate, x, y. Now here's the crucial part. Every vector, every arrow has two key properties, a length and a direction. Keep those two things in your head because they are about to become very important.
All right, that length we just talked about, it's got a special name, the modulus. You write it with those absolute value bars around the z. And how do we find it? Well, take a look at that formula. Does it look familiar? It should. It's literally just the Pythagorean theorem. It's the direct, straight-line distance from the origin out to our point. Let's try a real example. Let's take the number z equals -3 plus 2i. To find its modulus, its size, its length, we just plug in the numbers. We square the real part, -3, square the imaginary part, 2, add them up, and take the square root. The length of this vector is the square root of 13. See? Now we have a solid way to measure how big a complex number actually is.
Okay, so now that we're thinking of numbers as these cool arrows with both length and direction, a really interesting question pops up. What happens when we do arithmetic? What does it actually look like when you add or subtract in this new dimension?
First, let's look at the algebra. And honestly, it could not be simpler. To add two complex numbers, z1 and z2, you just add their real parts together, and then you add their imaginary parts together. It's totally straightforward. But, and this is the really cool part, check out what this looks like visually. If you draw the two vectors for z1 and z2, and then you complete the parallelogram that they form, the answer, their sum, is just the main diagonal of that shape. It's this beautiful visual rule called the parallelogram law. How awesome is that? And guess what? Subtraction is pretty much the same deal, algebraically. You just subtract the real parts, and then subtract the imaginary parts. Another way to think about it is you're just adding the negative of the second vector, which really just means you flip its direction 180 degrees. And geometrically, this is just brilliant. The vector for z1 minus z2 is not an arrow from the origin. Instead, it's the arrow that connects the tip of z2 to the tip of z1. Think about it. It represents the exact path, both the distance and the direction you'd need to travel to get from point z2 to point z1.
So, what's the big picture here? What does all this geometry and all these arrows really mean? Let's tie it all together and see why this way of thinking is just so powerful.
It really all comes down to this idea. The point is that complex numbers aren't some weird, separate thing that mathematicians just invented for fun. They're a natural extension of the real numbers we already know and love. It feels less like an invention and more like a discovery of a dimension that was there all along.
So why should you care? Because this turns abstract algebra into something you can actually see. All of a sudden, adding numbers isn't just a calculation. It's about building a shape. Subtracting is about finding a path between two places. And this intuitive visual understanding, it is the absolute foundation for tons of applications in physics, engineering, all the hard stuff.
So I want to leave you with this one last thought. We just found a beautiful, elegant geometric shape hidden inside something as simple as addition. It really makes you wonder, right? What other incredible mathematical truths are out there, just waiting for us, not to calculate them, but to actually see them?